Hey everybody, welcome to this video on hyperspectral imaging. So in a previous video we talked about some of the trade-offs between spatial resolution, temporal resolution, and spectral resolution. And we talked about how satellite sensors might be optimized to obtain one of those types of resolution. So hyperspectral imaging is a case where sensors or satellite missions are optimized for spectral resolution. And as the name implies, hyperspectral imaging is images that are collected in many different spectral bands, often hundreds of spectral bands, with a spectral resolution or bandwidth that is the resolution is higher and the bandwidth is smaller than typical imaging. So for example, we're talking about 0.01 micron bandwidth intervals, as opposed to perhaps 0.5. So maybe we're talking about 100 or 50 times smaller bandwidth intervals. And just like with any multispectral imaging, these are, of course, images of the same thing. They have the exact same footprint. They tend to have the exact same pixel size, right? And they're just stacked. It's a stack of replicate images of the same thing, each one taken in a slightly different wavelength interval of light. And that's what hyperspectral imaging is. So one example of a hyperspectral sensor is AVIRIS, the Advanced Very High Resolution Radiometer. This sensor is actually airborne. It flies on a NASA plane and can be chartered essentially for different projects. Now the benefit of flying in a plane, of course, is that you are much lower down. So the same number of photo sites on a detector chip will correspond to much smaller pixel sizes on the ground, as we talked about in the previous video. So for AVIRIS in particular, its instantaneous field of view is about 20 meters, so it generates a roughly 20-meter pixel size. And by scanning back and forth, its total field of view is about 11 kilometers. So it produces relatively high resolution data, high spatial resolution, and spectral. And so here's a comparison here's an example of what the data looks like. So it's a spectral reflectance curve here, or an atmospheric transmission curve. Here's wavelength across the bottom, and 224 spectral bands for AVIRIS. They're so narrow they can hardly even be displayed here, right? They're so narrow, they're just sampling the spectral reflectance curve into very tiny intervals. And for comparison, this figure shows the Landsat 6 bands. So here's blue, green, red, and near infrared. You see how much wider those are. The red band on Landsat 6 probably includes 10 AVIRIS bands or more. So that's an example of a hyperspectral sensor that has both very high spectral and spatial resolution. A different example is a satellite that's no longer in service. It's called SeaWiFS, or a sensor called SeaWiFS. And this was designed specifically to measure ocean productivity, and to do that by measuring the density of chlorophyll. And because the goal was to capture the whole ocean, essentially, they needed a very large footprint, right? And they could tolerate low spatial resolution. So they're able to put this on board a satellite, fly high, have relatively few photo sites on the detector, and therefore have big pixels, pixel sizes around 1 kilometer. And at the same time as doing that, they were able to have relatively high spectral resolution. They couldn't collect 224 bands, but they were able to collect 8 different bands that were each more narrow than a typical satellite, or like Landsat, might collect. So for example, here's the blue interval is divided into 2 different bands, right? Green is divided into 2 different bands. So the bandwidths are bigger than AVIRIS, but smaller than Landsat, for example. And importantly, they are targeted at unique features of the chlorophyll reflectance spectra. So let's have a look at that here. So on the top, I've shown two reflectance spectra, one of green algae, which has a ton of chlorophyll in it, and one of pure water. And these are collected from AVIRIS, okay? So in this case, the spectral bands are so tiny that you can't even see the dots, right? There's, many, many different dots in this line. And we see the full shape of the spectral reflectance curve, every little detail, because we have so many spectral bands. There's many data points that are making up this line. Okay, below in example 2, we have chlorophyll and water signatures collected from SeaWiFS, okay? And as I just mentioned, there's I think there was 8 spectral bands. We've only got 5 of them shown here on this plot. But here's what a low chlorophyll or a water sample looks like in SeaWiFS, right? You only have 1, 2, 3, 4, 5 data points connected by lines. And you can see that this yellow line does actually capture essentially what this blue line would look like if you only captured it with those 5 data points. It starts high and then goes low. In contrast, the high chlorophyll samples essentially do the opposite. They start low and they go high or kind of level off. And keep in mind the 6 data points here are capturing these different points. So we're capturing one about here, capturing one about here around 440 near this peak, a couple more in here, and then we got a really important one out at 560 capturing this peak. And so we see when the sample has high chlorophyll, we end up with pretty high values out here, which are capturing this peak in the chlorophyll or green algae spectrum. So the take-home message here is that hyperspectral imagers can have different approaches. They can have a lot of bands or they can have a few bands. In the case of AVIRIS, it's very versatile. You could do hyperspectral imaging of anything, but it's by plane. So you have basically no repeat time, right? You fly the plane once and that's probably it. Whereas SeaWiFS, they were able to pick, a very few but narrow bands that were really intended to measure one thing, which was chlorophyll, over a very broad area. So thanks for listening and see you in class.